Hello, my name is Nurul Atirah binti Jamridin, and in this video, I will be presenting a topic called thermal conductivity enhancement of carbon nanotube arrays, and bonded carbon nanotube network. Without further ado, let's get started. First is meaning of carbon nanotubes. Carbon nanotubes, which is short formed as CNTs, are long considered as a promising material for thermal applications. Carbon nanotubes are cylindrical molecules that consist of rolled-up sheets of single-layer carbon atoms, which is known as graphene. Next is problem statement. The first problem statement is the limited contact area at the interface, and some short CNTs in the array are not in contact to the other layer. Second is the low density, which is low volume fraction of CNTs of the CNTs in the CNT array. There are three objectives. The first one is to demonstrate a self-assembly method to fabricate bonded CNT networks. Second is to present the method to deposit carbon on the CNTs. The third one is to investigate the thermal properties of the samples. Secondary CNT growth. For the growth of secondary CNTs, nickel nitrate was dissolved in acetylene at a concentration of 0.01 mega as the catalyst precursor. The catalyst precursor was cast onto the vertical CNT array at a dose of 10 micrometer per 1 cm squared. The growth was carried out inside a homemade tube furnace. The furnace pressure was kept at atmospheric pressure during growth. Temperature was raised up to 700 degrees Celsius under 70 SCCM H2 and 200 SCCM AR atmosphere. When temperature reached 700 degrees Celsius, ethanol vapor was introduced into the furnace through a bubblery as the carbon source. Growth process took 15 minutes at 700 degrees Celsius, after which the ethanol vapor is cut off and samples were then cooled down to room temperature. In figure A and B shows the first growing vertically aligned CNT film by PECVD on silicon substrate as explained, and 3D CNT sample respectively. Carbon deposition on carbon nanotube and 3D carbon nanotube. In order to deposit carbon on a 3D CNT and CNTs, samples were placed in a filtered kinetic vacuum or FCVA deposition system. A schematic of the FCVA deposition system is shown in this figure, and the detail of deposition can be found in the supplementary file. This system is a well-known method to deposit high-energy metal and carbon ions on substrates. To accelerate carbon ions and to confine the coating around and on top of the 3D CNT and CNT rays, a negative pulse bias was used. As shown in these two figures, C ions were deposited on tip of CNTs and secondary CNTs and forms a layer of amorphous carbon, AC, on top of the 3D CNT network. In this case, carbon ions mainly were absorbed on top of the 3D CNT network because of existing of high density of the secondary CNTs on top and applying the negative pulse bias on them. As shown in figure 3, in the case of deposition of C on the CNT arrays, a C layer and sphere was formed on the CNTs because of the high energy positive carbon ions were accelerated to the side walls and tips of the tubes. As deposition continues, the nanosphere on the tips of the CNTs increased in size rapidly because of the higher charge density on the tips as shown in this figure 6a. The top layers were formed on top of the samples that adhere very well by the covalent bond to the tips and the side walls of the tubes. Structure characterization. SEM images were taken in an LEO1550 Gemini field emission scanning electron microscope, transmission electron microscopy, high resolution TEM, scanning TEM, and energy differsive X-ray spectroscopy. Line scans were carried out using Tech9 X-Twin TM equipped with EDAX silicon lithium detector. A WITEC Raman system with a laser wavelength 532 nm was used to obtain the Raman spectrum. PPR characterization. PPR technique was employed to investigate the thermal conductivity of 3D CNT network and C or CNT nanocomposite. PPR was first used to measure the thermal conductivity of silicon dioxide thin film. Since then, it has been widely used to examine the thermal properties of films. To enhance the heat absorption, a 250 nanometer gold layer is evaporated on the surface of the samples. The sample is first excited by the NDYAG laser pulse at the repetition rate of 10 Hz with 3 mm spot size, pulse energy 30.3 mJ and 7 nanosecond pulse width. This causes a fast rise in the surface temperature and then followed by a realization. 1 mW continuous probe beam with a spot size of about 20 micrometer is focused on the center of the pump beam to monitor the changes in light reflection from the metal surface. Since surface temperature and reflectivity of gold are inversely linearly related, the temperature excursion profile is sub-microsecond. Temporal resolution can be obtained by capturing the changes in reflected probe beam. Because the realization time is governed by the thermal properties of the underlying layers, by curve fitting the temperature excursion profile with a 4-layer, one-dimensional heat conduction model, one can extract the thermal conductivity of TIM. Figure 4a is the SEM images of CNTs obtained from PECVD growth. They are well aligned vertically into an array. These CNTs have fairly uniform diameters around 150 nm. The length of the CNTs are around 7 micrometers with slight differences among them. Image processing of several top-view SEM images of the CNT array was used to measure surface area fraction of the CNTs and then volume fraction of the CNTs was estimated. The average volume fraction of CNTs is calculated about 10%. After secondary growth process in the tube furnace, a network of CNTs is constructed as shown in Figure 4b. It can be seen in the cross-sectional view of SEM images that space in the CNT array is filled up by high density of finer secondary CNTs, which exhibits diameters in the range of 8 to 20 nanometers. Meanwhile, in the top view, the sample surface was completely covered by the secondary CNTs. The secondary CNTs have length up to several tens of micrometers and a widening morphology. Thermal characterization. The normalized surface temperature profiles for the samples and their fitted curves are shown in this Figure 8. To compare experimental data in this study with the primary CNT, we also show the normalized surface temperature of the samples. In Figure A, as the direct gold deposition on the primary CNT cannot cover the surface of the sample, the gold foil was used to capture photothermal signal. For the 3D CNT network, the thermal conductivity of the sample is increased by about 40%. The thermal conductivity of the 3D CNT network is contributed from the intrinsic thermal conductivity of the CNT, the intrinsic thermal conductivity of the secondary CNT, and the thermal conductivity of the air gap is filling factor of the tubes. The growth of the secondary CNT decreases the air volume fraction and enhances thermal conductivity of the 3D CNT network. The other reason for thermal conductivity enhancement is that the secondary CNT works as extra channels to transfer heat at the top surface downward through the CNTs. For the C and CNT sample, the improvement on the thermal conductivity is about 70%. After C deposition, the diameter of the tubes increases and the air volume fraction decreases to about 60%, and the thermal conductivity increases. The C layer in this deposition technique inherit very well to the tips and side walls of the CNTs, as the carbon ions formed strong covalent CC bond and having very low thermal contact resistance between them. The C layer around the CNTs also acts as an extra heat channel to transfer heat to the CNTs and substrate, thus boosting the array's thermal conductivity. In conclusion, this two-step growth method was developed and successfully fabricated 3D CNT network based on the CNT array. In this fabrication method, the air volume fraction is effectively decreased. The thermal conductivity of the samples was measured by PPR technique, and 4-layer model for the first time was used to extract thermal conductivity. The samples were covered by a C layer, and the layer adhered very well to CNTs by strong covalent bond with low thermal contact resistance.